Welcome back, and in this lesson I want to talk about how routing works within a VPC and introduce the Internet Gateway, which is how we can configure a VPC so that data can exit to and enter from the AWS public zone and public internet. Now this lesson will be theory, where I'm going to introduce routing and the Internet Gateway, so the architecture behind both those things, as well as jump boxes, also known as bastion hosts. In the demo lesson which immediately follows this one, you'll get the opportunity to implement an Internet Gateway yourself in the Animals for Life VPC and fully configure the VPC with public subnets that allow you to connect to that jump box. So let's get started, we've got a lot to cover. A VPC router is a highly available device which is present in every VPC, both default or custom, which moves traffic from somewhere to somewhere else. It runs in all of the availability zones that the VPC uses. You never need to worry about its availability. It simply works. The router has a network interface in every subnet in your VPC, the network plus one address of the subnet. By default, in a custom VPC, without any other configuration, the VPC router simply routes traffic between subnets in that VPC. If an EC2 instance in one subnet wants to communicate with something in another subnet, the VPC router is the thing that moves the traffic between the two. Now the VPC router is controllable. You create route tables which influence what to do with traffic when it leaves a subnet. So just to be clear, the route table that's associated with a subnet defines what the VPC router will do when data leaves that subnet. A VPC is created with what's known as a main route table. If you don't explicitly associate a custom route table with a subnet, it uses the main route table of the VPC. If you do associate a route table that you create with a subnet, then when you associate that, the main route table is disassociated. A subnet can only have one route table associated with it at any one time, but a route table can be associated with many subnets. A route table looks like this in the user interface. In this case, this is the main route table for this specific VPC. And a route table is just a list of routes. This is one of those routes. When traffic leaves the subnet that this route table is associated with, the VPC router reviews the IP packets. And remember, I said that a packet had a source address and a destination address, as well as some data. Well, the VPC router looks at the destination address of all packets leaving this subnet. And when it has that address, it looks at the route table and it identifies all of the routes which match that destination address. And it does that by checking the destination field of a route. This destination field determines what destination the route matches. Now, the destination field on a route could match exactly one specific IP address. It could be an IP with a /32 prefix, and remember, that means that it matches one single IP. But the destination field on a route could also be a network match, so matching an entire network of which that IP is part. Or it could be a default route. Remember, for IP version 4, I mentioned that 0.0.0.0/0 matches all IP version 4 IP addresses. That's known as a default route, a catch-all. In the case where traffic leaving a subnet only matches one route, then that one route is selected. If multiple routes match, so maybe there's a specific /32 IP match, maybe there's a /16 network match, and maybe there is a 0.0.0.0/0 default match, well then the prefix is used as a priority. The higher the prefix value, the more specific the route is, and the higher priority that route has. So the higher the prefix, all the way up to the highest priority of /32, that is used to select which route applies when traffic leaves a subnet. Once we get to the point where a single rule in a route table is selected, either the sole route that applies or the one with the highest priority, then the VPC router forwards that traffic through to its destination, which is determined by the target field on the route. And the target field will either point at an AWS gateway, or it will say, as with this example, local. And local means that the destination is in the VPC itself, so the VPC router can forward the traffic directly. All route tables have at least one route, the local route. This matches the VPC CIDR range, and it lets the VPC router know that traffic destined for any IP address in the VPC CIDR range is local and it can be delivered directly. If the VPC is also IP version 6 enabled, it will also have another local route matching the IP version 6 CIDR for the VPC, as is the case with this example. That bottom route beginning 2600, that is an IP version 6 local route. That's the IP version 6 CIDR of this specific VPC. Now these local routes can never be updated. They're always present and the local routes always take priority. They're the exception to that previous rule about the more specific the route is, the higher the priority. Local routes always take priority. For the exam, remember that route tables are attached to 0 or more subnets. A subnet has to have a route table. It's either the main route table of the VPC or a custom one that you've created. A route table controls what happens to data as it leaves the subnet or subnets that route table is associated with. Local routes are always there, uneditable, and match the VPC IP version 4 or 6 CIDR range. For anything else, higher prefix values are more specific and they take priority. The way that a route works is it matches a destination IP, and for that route, it directs traffic towards a specific target. Now, a default route, which I'll talk about shortly, is what happens if nothing else matches. Now, an internet gateway is one of the most important add-on features available within a VPC. It's a regionally resilient gateway which can be attached to a VPC. I've highlighted the words region and resilient because it always comes up in the exam. You do not need a gateway per availability zone. The internet gateway is resilient by design. One internet gateway will cover all of the availability zones in the region which the VPC is using. Now, there's a one-to-one relationship between internet gateways and the VPC. A VPC can have no internet gateways, which makes it entirely private, or it can have one internet gateway. Those are the two choices. An internet gateway can be created and not attached to a VPC, so it can have 0 attachments, but it can only ever be attached to one VPC at a time, at which point it's valid in all of the availability zones that the VPC uses. Now, the internet gateway runs from the border of the VPC and the AWS public zone. It's what allows services inside a VPC which are allocated with public IP version 4 addresses or IP version 6 addresses to be reached from the internet and to connect to the AWS public zone or the internet. And of course, the AWS public zone is used if you're accessing S3, SQS, SNS, or any other AWS public services from your VPC. Now, it's a managed gateway, and so AWS handles the performance. From your perspective as an architect, it simply works. Now, using an internet gateway within a VPC, it's not all that complex. Here's a simplified VPC diagram. First, we create and attach an internet gateway to a VPC. This means that it's available for use inside the VPC. We can use it as a target within route tables. So then we create a custom route table and we associate it with the web subnet. Then we add IP version 4 and optionally IP version 6 default routes to the route table, with the target being the internet gateway. Then finally, we configure the subnet to allocate IP version 4 addresses and optionally IP version 6 by default. And at that point, once we've done all of those actions together, the subnet is classified as being a public subnet. And any services inside that subnet with public IP addresses can communicate to the internet and vice versa, and they can communicate with the AWS public zone as long as there's no other security limitations that are in play. Now, don't worry if this seems complex. You'll get to experience it shortly in the upcoming demo lesson. But before that, I want to talk about how IP version 4 addressing actually works inside a VPC, because I've seen quite a few difficult questions on the exam based around IP version 4 addressing, and I want to clarify exactly how it works. So conceptually, this is how an EC2 instance might look if it's using IP version 4 to communicate with a software update server of some kind. So we've got the instance on the left with an internet gateway in between, and let's say it's a Linux EC2 instance trying to do some software updates to a Linux update server that's located somewhere in the public internet zone. So the instance has a private IP address of, let's say, 10.16.16.20. And it also has an IP version 4 public address that's assigned to it of 43.250.192.20. Only that's not how it really works. This is another one of those little details which I try to include in my training courses because it really comes invaluable for the exam. What actually happens with public IP version 4 addresses is that they never touch the actual services inside of VPC. Instead, when you allocate a public IP version 4 address, for example to this EC2 instance, a record is created which the Internet Gateway maintains. It links the instance's private IP to its allocated public IP. So the instance itself is not configured with that public IP. That's why when you make an EC2 instance and allocate it a public IP version 4 address, inside the operating system, it only sees the private IP address. Keep this in mind for the exam. There are questions which will try to trip you up on this one. For IP version 4, it is not configured in the OS with the public IP address. So let's look at the flow of data. How does this work? Well, when the Linux instance wants to communicate with the Linux software update server, it creates a packet of data. Now, obviously, it probably creates a lot of packets, but let's focus on one for now because it keeps the diagram nice and simple. The packet has a source address of the EC2 instance and a destination address of the Linux software update server. So at this point, the packet is not configured with any public addressing. This packet would not be routable across the public internet. It could not reach the Linux update server. That's really important to realize. Now, the packet leaves the instance, and because we've configured a default route, it arrives at the Internet Gateway. The Internet Gateway sees that this packet is from the EC2 instance because it analyzes the source IP address of that packet, and it knows that this instance has an associated public IP version 4 address, and so it adjusts the packet. It changes the packet's source IP address to the public IP address that's allocated to that instance, and this IP address, because it's public, is routable across the internet. So the Internet Gateway then forwards the updated packet onto its destination. So as far as the Linux software update server is concerned, it's receiving a packet from a source IP address of 43.250.192.20. It knows nothing of the private IP address of this EC2 instance. Now, on the way back, the inverse happens. The Linux software update server wants to send a packet back to our EC2 instance, but as far as it's concerned, it doesn't know about the private address. It just knows about the public address. So the software update server sends a packet back addressed to the instance's public IP address with its source address. So it thinks that the real IP address of the instance is this 43.250.192.20 address. Now, this IP address actually belongs to the Internet Gateway, and so it travels over the public internet and it arrives at the Internet Gateway, which then modifies this packet. It changes it. It changes the destination address of this packet from the 43 address to the original IP address of the EC2 instance. And it does this because it's got a record of the relationship between the private IP and the allocated public IP. So it just changes the destination to be the private IP address of the instance, and then it forwards this packet through the VPC network to the original EC2 instance. So the reason I wanted to highlight this is because at no point is the operating system on the EC2 instance aware of its public IP. It just has a private IP. Don't fall for any exam questions which try to convince you to assign the public IP version 4 address of an EC2 instance directly to the operating system. It has no knowledge of this public address. Configuring an EC2 instance appropriately using IP version 4 means putting the private IP address only. The public address never touches the instance. For IP version 6, all addresses that AWS uses are natively publicly routable. And so in the case of IP version 6, the operating system does have the IP address version 6 address configured on it. That's the publicly routable address. And all the internet gateway does is pass traffic from an instance to an internet server and then back again. It doesn't do any translation. Now, before we implement this in the demo lesson, I just want to briefly touch upon Bastion hosts and jump boxes. At a high level, Bastion hosts and jump boxes are one and the same. Essentially, it is just an instance in a public subnet inside of VPC. And architecturally, they're used to allow incoming management connections. So all incoming management connections arrive at a Bastion host or jump box, and then once connected, you can then go on to access internal only VPC resources. So Bastion hosts and jump boxes are generally used either as a management point or as an entry point for private-only VPCs. So if your VPC is a highly secure private VPC, you'll generally have a Bastion host or a jump box being the only way to get access to that VPC. So it's essentially just an inbound management point. And you can configure these Bastion hosts or jump boxes to only accept connections from certain IP addresses, to authenticate with SSH, or to integrate with your on-premises identity servers. You can configure them exactly how you need, but at a real core architectural level, they are generally the only entry point to a highly secure VPC. And historically, they were the only way to manage private EC2 instances. Now, there are alternative ways to do that now, but you will still find Bastion hosts and jump boxes do feature on the exam. Okay, so that's all of the theory that I wanted to cover in this lesson. It's now time for a demo. In the next lesson, we're going to implement the Internet Gateway in the Animals for Life VPC. We'll create it, we'll attach it to the VPC, we'll create a custom route table for the web subnets, we'll create 2 routes in that route table, one for IP version 4 and one for IP version 6, and both of these will point at the Internet Gateway as a target. We'll associate that route table with the web tier subnets, configure those subnets to allocate public IP version 4 addresses, and then launch a Bastion host into one of those web subnets. And if all goes well, we will be able to connect to that instance using our SSH application. So I think this demo lesson is going to be really interesting and really exciting, and it's the first time that we're going to be stepping through something together that we could qualify as production-like. It's something that you could implement and would implement in a production-ready VPC. So go ahead, complete this video, and when you're ready, join me in the demo lesson.